All right, for assignment number 5, the first thing that they want us to do is fill out this table. So it says complete the table and use the result to estimate the limit, and then use a graphing utility to graph to sort of verify your result. So if we were to just plug in 0 right now, we would get 0 over 0. So that's why we're kind of investigating like this. And remember, when you're filling out a table, you can type the function into y1 just to save you a bit of typing on the other end. So that's what I'm doing right here. Sine of 4x over sine of 3x. And then you can have the calculator evaluate. So alpha trace gets you y1. And I can just say, all right, what's y1 of negative 0.1? And I'm going to round let me split screen here. I'm going to round this just to 3 places, I think. Okay, and then I can say the next one was negative 0.01. Kind of same thing. If I round to only 3 places, I guess I'm kind of getting, hold on. Oh, you know what? I'm in degree mode. I was like, why am I getting the answer? Sorry. Make sure you're in radian mode. Let me go back up. I mean, the answer is 4/3, but I'm not supposed to be getting that this quickly. So, whoops. Okay. So when I was in degree mode, that was like putting in negative 0.1 degrees is so much smaller than putting in negative 0.1 radians when you're plugging in. So anyway, and then this one is, so now to 3 places. I'm back here anyway. Negative 0.001, 1.333. And if we do this on the other side, so I'm going to delete, I'm going to start at the end. So what if because it doesn't make sense to start when you're really close and go further out. So what if we plug in 0.1? So, okay, it looks like we're getting kind of the same thing, y-axis symmetry. What if we plug in 0.01, 1.333, and same thing if I plug in the positive, save time here. The next one will be that. So what does this look like? Well, yeah, this looks like 1 1/3 or 4/3 to me as we're getting closer and closer to 0 from both sides. If I look at this graph, I'm just going to zoom 6. We're approaching 0 from both sides. I definitely zoomed it in here in my screenshot. But yeah, this looks like it's approaching 4/3. There's a bit of a gap there because we don't have a point at 0 actually. Okay, so yes, I'm going to say that this limit is probably 4/3. What if we're not doing things numerically? Well, we would need to use L'Hopital's rule to start working on this and get it to something that direct substitution works for. All right, so evaluate the limit using techniques from chapters 1 and 3 for part A, and then for part B using L'Hopital's rule. So part A, if I'm not allowed to use L'Hopital's, I'm going to try, if I try direct substitution, I get 0 over 0, but I can factor this a bit. So when I can factor and cancel, I usually, you have a choice for how you're going to evaluate the limit. Oops, don't forget about your limit notation. I would do this over L'Hopital's anyway. So I can cancel out the x minus 4s, and then when I try direct substitution, I get 3 over 8. So that's easy. If I'm supposed to use L'Hopital's method, first I want to show that the limit as x approaches 4 of 3 times x minus 4 equals 0. And that equals the limit as x approaches 4 of x squared minus 16. So this is how we have to show this now, instead of saying, oh, this equals 0 over 0. Like that, this is not actually a thing, a mathematical correct concept. So that's why we're saying, well, the top and the bottom limits are both 0. So we're going to use L'Hopital's rule. So the limit as x approaches 4 of the original, which I'm going to distribute the 3 through. So here's the original limit. L'Hopital's rule says that can be equal to the limit as x approaches 4 of the derivative of the top, which is 3, over the derivative of the bottom, which is 2x. Try direct substitution again, and you get 3 over 8. If I do direct substitution after one round of L'Hopital's and I get 0 over 0, then I do L'Hopital's rule again, and you keep going until you can get something that's not in an indeterminate form. Okay, what about number 7? Excuse me. If you plug in 6, you get 4 minus 4 on top, 6 minus 6 on the bottom. So that's why we're working on this, because 0 over 0 is an indeterminate form. So what did we do to work on this? We rationalized the numerator. So we multiply, let me write this original down. Okay, here's the original problem. We multiply by the conjugate of the numerator, so square root of x plus 10 plus 4 in the top and the bottom. All right, remember to keep your limit notation. And so when you multiply these two conjugates together, you get x plus 10 minus 16. And you don't actually distribute this through. It's just the quantity x minus 6 times the quantity x square root of x plus 10 plus 4. The reason you don't distribute anything down here is because this numerator is x minus 6. That's equal to x minus 6. So that cancels with that. So now it's the limit as x approaches 6 of just 1 over the square root of x plus 10 plus 4. Try direct substitution into that, and you get 1 over square root of 16, which is 4, plus 4. So you get 1/8. Okay, L'Hopital's rule says, let's show that we get 0 over 0. So as x approaches 6, of the square root of x plus 10 minus 4, that equals 0. And that also, 0 is also equal to the limit as x approaches 6 of x minus 6. So the original limit, which is this, is equal to the limit as x approaches 6 of the derivative of the top over the derivative of the bottom. So x plus 10 to the 1/2 is going to become 1/2 x plus 10 to the negative 1/2 times the derivative of x plus 10, which is just 1. Derivative of 4 is 0. And then the derivative of x minus 6 is just 1. So try direct substitution into this. Now this is a negative exponent, so it's going to be 1 over 2 square root of 6 plus 10. 1 over 2 times 4 is 1 over 8. So that's that. All right, for number 8. Okay, number 8, this was one of those kind of tricky ones that we said, like, well, actually, let's see. So remember we had the limit as x approaches 0 of, like, if this were sine of 6x over 6x, then I would have the limit equal to 1. So we can I just realized a different way to do this. I did it kind of a crazy way with identities in my original answer key, but I just realized I'm going to change this up. I want the 4x to equal 6x. So what do I need to multiply? You can only multiply something in to make this happen. Well, what do I need to multiply that by? So like I need a k times 4x to equal 6x. There we go. I need some sort of constant. So what would k have to equal? 6x over 4x. All right, so what does that mean? K would have to equal 3 over 2. So what I want to happen is I have sine of 6x here. I want this to be a 6x down here. So I'm going to do 4x, and I'm going to say multiply that by 3 over 2, because that would make that 6x, right? And you can't just multiply something in the bottom. You also have to multiply it in the top. So the constant that I multiply in the top, I'm going to pull out in front. And the constant that I multiplied in the bottom, I'm going to keep it down there and go ahead and multiply it in. 3/2 times 4x is 6x. Now this limit is one that we memorized back in chapter 1. It's equal to 1. And so this is 3/2 times 1, which is 3/2. Another way that I did this was, and again, I don't think this would probably not come to mind as quickly. I used a sum formula for the sine of 6x. I made it 4x plus 2x. But now that I think about that, this matches more of what we did in chapter 1. All right, so what if we use L'Hopital's? Because that would be a lot easier. So first show your limits. The limit as x approaches 0 of sine of 6x. The sine of 0 is 0. And that equals the limit as x approaches 0 of 4x. So that means we can use L'Hopital's rule. So the limit as x approaches 0 of the sine of 6x over 4x has to equal the limit as x approaches 0 of the derivative of each of these. So this is going to be 6 cosine of 6x over 4. Now try direct substitution there. You get 6 cosine of 0 over 4. Cosine of 0 is 1. So 6 over 4 is 3 over 2. So we have to use a little bit of trickery to do it without L'Hopital's rule. L'Hopital's is a bit more straightforward. All right. I'm not sure if I'm going to get through all of these problems. I'll just see how far I can get before office hours start. So evaluate the limit using L'Hopital's if necessary. N is always a positive integer for exercise 18. All right. So first thing I want to do is factor this expression, because if I can just cancel and then use direct substitution, I'll be good. So yeah, if I just use direct substitution now with just the x plus 1, I've got 3 plus 1 is 4. No L'Hopital's needed. For this one, I can do L'Hopital's. So because I would get, if I plug in 5, I would get 0 over 0. So first remember to show the limit as x approaches 5. It says 5 from the left because of the domain of this little half circle here. Of the square root of 25 minus x squared, that's equal to 0. And 0 is also equal to the limit as x approaches 5 on the left of x minus 5. So take your original limit. I want to rewrite it as 25 minus x squared to the 1/2 just to help me with my derivatives. That equals the limit as x approaches 5 on the left of 1/2. 25 minus x squared to the negative 1/2 times the derivative of 25 minus x squared, which is minus 2x, all over 1. Derivative of x minus 5 is 1. Can we evaluate at this point? We might want to clean things up a little bit just so we don't get the wrong answer when we evaluate. So 1/2 times negative 2x is just negative x. And this negative exponent is going to send this square root of 25 minus x squared to the denominator. Now, if I plug 5 in into this, I'm getting negative 5 on top and 0 on the bottom. And remember, that doesn't mean we need L'Hopital's rule again. It means that this limit doesn't exist. The graph on the left of 5 must be heading to negative infinity. So this limit does not exist, and I can say how it does not exist because it's going, it's unbounded in the negative direction. All right, for this one, if I plug in 0, I get 1 minus 1 minus 0 over 0. So I'm going to L'Hopital's. Oops. So first I want to show the limit as x approaches 0 of e to the x minus 1 minus x. That's equal to 0. 0 is also the limit as x approaches 0 of x. So I'm writing the original problem. I'm just going to distribute this negative. And now I'm going to take derivatives. The limit as x approaches 0 of e to the x, 1 becomes 0, x becomes 1 over 1. Plug that in, you get e to the 0 plus 1 over 1. So that's 1 plus 1 is 2. All right. Let's see. How far can I get? I don't think I can get through all of these. I'm going to do, I think, 2 more problems, and then we'll go from there. Arc sine over x. So when you plug 0 in, you're saying sine of what angle equals 0? So that is 0 and 0 on the bottom. So show my L'Hopital's. And the limit as x approaches 0 of arc sine x, that equals 0. And that's also equal to the limit as x approaches 0 of x. And then this, oops, not infinity. The limit as x approaches 0 of arc sine x over x. So we need to remember how to take the derivative of arc sine. Remember, there's a formula for that. It's just arc sine x. So the formula is, think about what the integrals look like, right? This is the integral setup when we know, oh, okay, that's arc sine. So go backwards. That means the derivative of arc sine is u prime. So x, the derivative of x is 1 over the square root of a squared minus u squared. So a is just 1 because this is the arc sine of x over 1. So 1 minus x squared. And then the derivative of x is just 1. So if I plug 0 back into this, I get 1 over square root of 1 minus 0. So that's equal to 1. All right, I'm going to actually stop this video here, and then I will continue on in the next video when I have more time.